All right, this next example we have is our first volume of revolution problem. So we are asked to rotate the region enclosed by y equals 0, y equals the square root of x over 1 to 0 about the x-axis and determine its volume. Excuse me. So first thing to do for any of these problems, first thing is sketch the region. Absolute first thing to do every single time, sketch the region. So let's just write that down, sketch region. So I'll start by drawing my axes, so y-axis, x-axis, and in particular, y equals 0 is the x-axis, so I'm just going to label that y equals 0 just so we're all aware that yes, it is sketched, and y equals the square root of x, that looks something like that. Over 0 to 1 about the x-axis to determine its volume. So let's just say, well, we know 0's here, so let's say x equals 1 is, we'll exaggerate it, we'll just say it's right there. Okay, so this region that we're asked to rotate is this. Now, one thing that can be a struggle for some people, sometimes, not even all the time, is identifying the region. This region, I would say, is fairly straightforward to identify, but later on there can be some ambiguity. I mean, there actually isn't any ambiguity. You just have to make sure you're reading the problem in the right way. And what I mean by that is you want to make sure that the equations listed do actually constitute the boundary of your region. So for instance, y equals 0 is the lower boundary. So I know that this has to be a boundary. I know that y equals the square root of x must be a boundary. And I know we go from x equals 0, which is x equals 0 is this vertical line, the y-axis, and x equals 1 is this boundary. So all of your curves and your bounds, they should enclose a region. So make sure that's the case. If you identify a region or two regions and you're not sure which one's which, go through systematically and see what region actually is enclosed by all of the equations listed and your bounds. That should narrow it down to exactly one region, and then that is the region that you would rotate. Here, there's no other enclosed region, so this should, that's the one. So we are to rotate this about the x-axis. So I would just go ahead, and for me, I am very much used to just drawing a little symbol so that we know, and we don't have to keep rereading the problem. Okay, so if we're rotating about this axis, we can think about in the previous page, in the previous video, we thought about, oops, let's get an eraser here. We thought about this line segment that gets rotated about the axis. So it's this line segment. So in particular, it is perpendicular to the axis of rotation. It's perpendicular. So to this problem, I can draw a representative segment that will be rotated. So I can grab or just label some x value. So we're at some x value, x, and this line segment is what is going to be rotated. If you want to, you are more than welcome to draw a representative shape if it helps you. I don't necessarily think that is the most helpful, but for some people it certainly is. So if you feel like you should draw that, go for it. Okay, so what we need to know is that since this is the radius, we need to know what this distance is. Well, whenever we measure anything from the x-axis, we're allowed to call that distance a y. So if we're at some arbitrary x value, then the length of this line segment is the y value that corresponds to this x value on this curve, since that's where the line touches. It stops at the y value on this curve at this x value. So this means the radius, if we wanted things in terms of y, which we don't, but if we did, we would leave it as y. Because we're rotating about the x-axis, when we do disks and washers, if we rotate about a horizontal axis, we integrate with respect to x. And if we rotate about a vertical axis, we integrate with respect to y, which is the vertical variable. So for us, since we're rotating about the x-axis, which is a horizontal axis, we want to make sure that we are using our radius written in terms of x. So one thing that I'm going to erase this for, I'm going to erase this for a moment, and I'm also going to go ahead and just say that this is the radius. So if you want to write r, that's true, and then you want to sort of take it step by step, or all at once if you're comfortable with that, and get it into the variable that we actually need. So from this point, you could say, oh, well, that's the y value because it's attached to the x-axis. And then you can say to yourself, well, since we're rotating about a horizontal axis, we actually want this written in terms of x. And the relationship between y and x along this curve is this. So ultimately, our radius is y, which is then square root of x. So now we know that the volume is pi times the integral from start to finish, so 0 to 1, of our radius squared, dx. So our radius is the square root of x. So we have the integral x dx, which is just, when we integrate this, we should get pi over 2 for our final answer.